Our last speaker for the afternoon is Manfred Salmhofer from Heidelberg, who will talk about functional integrals for Bose-Fermi systems.
Thank you very much, Gordon. Can everyone hear me? Yes. Okay. Well, first I would like to thank my fellow organizers for inviting me to speak, so I didn't invite myself. In fact, I'm always happy to be quiet, but anyway. I will today speak about something very easy, which is, I believe, connected to something very hard, but I will just speak about the easy part. In fact, I thought it was so easy that I gave it to a master's student, Maximilian Nitschner, who is now at ETH doing his PhD. But there were some points which turned out not to be completely obvious. And this talk is not really for the experts, but maybe for the wider audience. You will see some maybe not so familiar looking integrals here, and maybe it's of interest to get into this subject. So, functional integrals for Bose-Fermi systems. So what are Bose-Fermi systems? That's the first question. So there's a lot of physical motivation for this. Of course, bosons and fermions are what we are made of, and they exist in nature both on the fundamental level of fundamental particles and also composite particles. And as a very general introduction, let me remind you that there is the so-called spin statistics theorem, which tells us that in 3+1 dimensions, under very general axioms, Bose and Fermi statistics are the only possibilities for identical particles, and integer spin corresponds to bosons, and particles with half integer spin are fermions. And okay, so this is actually a relativistic theorem on the level of non-relativistic quantum mechanics, which I will be discussing here. Well, it is just about the representation of the permutation group then. So we assume we have wave functions depending on particle coordinates and the spin variables, which I denote by the alphas. And so there are these two possibilities. If you permute the arguments by some permutation pi, either the function remains unchanged, so it's totally symmetric, or you get the sign of the permutation, and then it's totally antisymmetric. And the symmetric case are the bosons, the antisymmetric case are the fermions. And just to repeat it, I mean, I wouldn't be standing on this floor if there weren't Fermi statistics, so most of the stability of matter comes from Fermi statistics, the existence of metals and all kinds of things. And Bose statistics is crucial to understand many types of collective phenomena. Okay. So what are the specific systems we're interested in? I've written down here one. This is, for the moment, formal. I will explain things more carefully later. So you can think of a Hamiltonian. You have the typical quantum mechanical kinetic terms, and so we have particles. Oh, we have the same m. So this is a mass, and this is a number m. Sorry for that. So the Laplacian, and with different masses, but the first m particles have the same mass. The second n particle have the same mass, so they are identical. And so what I wrote down here is just an interaction which depends on these coordinates between them. So when these particles are at positions capital Xi and little xj, they have some interaction W, and I also put the coupling constant in front. Here, oops, I have to be careful. Okay, and then there are ellipses here out of laziness. Of course, you can also put interactions between these particles among themselves and these particles among themselves as well. And usually one rewrites this immediately in second quantized form, so one doesn't regard m and n as fixed necessarily anymore. And then you write it in terms of the Bose and Fermi creation annihilation operators. Here I wrote them already in Fourier space, and the kinetic terms are then just the familiar k-squared terms. And the interaction term would be the density of fermions times the density of bosons, and instead of capital X and little x, I now chose x and y. And the other terms would look correspondingly. So these are things which get studied, for instance, in Heidelberg in labs. So they mix some kind of fermions, lithium-6 and bosons, and they do all kinds of fascinating things with them. There is also a very well-known system, the so-called electron-phonon system, which has the general form that the bosons, well, they just have some omega of k, so which replaces this k squared. And the fermions can also have some other energy-momentum relation here. And then there is a term which is different from this one. This one, when you describe it pictorially, you would think of an interaction B going in, B coming out, F going in, F coming out. So maybe I should write it like this. This one is different. This is just you have a boson which scatters off a fermion. So this would then be something like that. And so this is another Hamiltonian. Of course, you can write them in position space, which I will do later anyway. So what is a perspective on these systems? These are very simple systems, seemingly. Electrons and phonons are very important. This is what I wrote down is the basic Hamiltonian, so-called Fröhlich model for electron-phonon interactions in some metal. And this is the basis of the standard theory of superconductivity. And the standard theory of superconductivity, I mean, it doesn't work in every case. I mean, high TCs are different, but if you take, for instance, lead superconductor, it doesn't only work, it is astonishingly accurate. Yeah? Because it's a simple mean field theory, and you can ask yourself, why is it so accurate? And I will come back to this shortly. And the first Hamiltonian atomic Bose-Fermi mixtures, well, there are lots of phenomena which I'm not going to discuss here because I have not much to say about them at this point. So there are lots of things, lots of phases that one can study, phases of matter. Mathematically, the major goals are, well, proving the existence of superconductivity at low temperatures. This is sort of the holy grail type goal. I just heard from Jérémy Unterberger that he has some ideas together with Jacques Magnin to make progress. So second goal, which is sort of way below this, is to prove Migdal's theorem. Migdal's theorem gives a reason why this theory is so accurate, but it doesn't show anything about symmetry breaking. And then even simpler goal is if you have a gapped system, then you want to know that certain decay properties remain valid when the interaction is switched on. And well, what do we want to do to get to these goals? Well, there are many approaches, but one is to use functional integral representations. They're also ubiquitous in physics. And the reason we use them here is simply we want to use the machinery of cluster expansions, and this machinery works best when the algebra your activities are in is commutative, and that is not the case for these operator algebras, which I just, in terms of which I formulated the Hamiltonians. And I will review this basically and give a simple derivation of the functional integral representation. I believe it is instructive. It is not very complicated, but not completely trivial. One reason is that the functional integral for the Bose particles is complex and oscillatory. And there is important work by Balaban, Feldman, Knörrer, and Trubowitz, who study the Bose gas with the aim of proving Bose-Einstein condensation. And they also, to start out with, they start with the algebraic formulation and then rewrite it as a functional integral. What I will do here is a much simpler case, much easier. And there is other previous work by Cindy Blois, who did her PhD thesis with Joel Feldman, 2015. She also studied functional integral representations using Duhamel formulas and showing certain analytic properties of effective actions. And so I give a simplified derivation of the functional integral and discuss a few applications. So as I said, I will do something easy, which is connected to all these hard questions. Okay, so now let's look at this mathematical setup. So for the experts, it's just the standard C-star algebraic framework of quantum statistical mechanics. And as usual, one has to regularize the model both at short and long distance, so ultraviolet and infrared. So in the infrared is standard statistical mechanics. You put the particles into some finite box, side length L, let's say, and we have a discrete Fourier spectrum. And for the short distance, you can either restrict all energies to be below a maximal energy or use a lattice. And the effect is always to make the one particle Hilbert space finite dimensional. The dimension is huge typically, so for instance 10 to the 25 if you think of a solid state system. And okay, so for what I talk, I will in this talk I will use the lattice. It's really not very important, but I don't require translation invariance or anything. Basically, you can think of this lattice as a set, and the graph structure of it is defined by the kinetic terms for the bosons and the fermions. And I will use this notation for a bilinear form of some functions which go from some set X into some algebra. Okay, so yeah, so this is part of the preliminaries of the setup. In this finitist setting, we have just a finite dimensional one particle Hilbert space, and the n particle spaces are the standard objects. The boson one is the symmetric tensor product, the fermion one is the exterior algebra, nth order. The dimensions are quite different. So here are the formulas for the dimensions. And then one introduces Fock space, so one allows for arbitrary particle numbers. So you take the direct sum of these Hilbert spaces, and it's all standard. The elements are then identified with sequences, psi n being in the corresponding n particle space. You have vacuum vectors, which are this psi 0, so the 0 space is just complex numbers. And the most important thing to remember for the following is that by our setup, the fermionic space is always going to be finite dimensional because, okay, the dimension is explicit to the number of lattice points. However, the boson space is infinite dimensional, and this means one has to be a little bit careful about some technical details. So then for the full space of bosons and fermions, we just take the tensor product. And then there is a dense subspace, which is often used, I mean, finite vectors, finite meaning that this sequence has only finitely many non-zero entries. Okay, so, and then operators on the tensor product. This is just notation, of course. Maybe the most important thing about this is this names, I call an operator purely bosonic if it acts only on the bosons, and purely fermionic if it only acts on the fermionic factor. And obviously these two types of operators commute with one another. And okay, so these are star algebras. And then bosons and fermions are in this algebraic setup specified by canonical commutation relations and canonical anti-commutation relations. So they are written here. And the main difference between these operators is that the boson operators are unbounded operators, and the fermion operators have norm bounded by 1. So they are much easier to deal with. And there's one important restriction which shows up in this, which I would like to mention. These are unit lattice normalizations. I told you before that I introduced an ultraviolet cutoff. This means the ultraviolet cutoff is 1. If you had a different cutoff, if you want to take an ultraviolet cutoff and take it to infinity, then there will be a prefactor here which goes to infinity. And this is a limit I cannot take, and I will not. So I will stick to this one here. Okay, so then the number operators are these quadratic pieces here. And then we define our Hamiltonians now in this setting. So the kinetic terms are just given by basically hopping matrices. The one for the bosons is called theta. The one for the fermions is called Q. I use different sets for bosons and fermions because they can have different internal indices, spins, and so on. And the object which you saw at the board at the beginning, so this F dagger F coupling to a boson, well, I generalize it slightly. I take the F dagger F, the local number, and I average it with some G. So G could also be just localizing it as a single point, but can also average it. Okay, so then we have a Hamiltonian which consists of two pieces, and sorry? Is there a question?
No, you can go.
Okay. So I call the first piece HB and the second HF, and you will notice HF is purely fermionic. That's just a kinetic term written in this fermionic notation. So let me write this down one last time. So this is really, just so that you remember this. This notation is always for such a bilinear object. And then we have a kinetic term for the bosons, and this is the term coupling the boson to the fermionic bilinear. So this is really the thing you also had on slide 1. And so the bosonic operator is, of course, unbounded. It is symmetric, and it extends uniquely to a self-adjoint operator on F. You will see the reason for this immediately. And the fermionic operator is bounded anyway. So, and then one does grand canonical ensemble. So one takes an inverse temperature and two chemical potentials for the bosons and for the fermions. And one just writes an operator K, which is H minus these chemical potentials, by which you can adjust the average number of particles. And well, obviously this is also a quadratic part, so if I take this difference, it's really just HB of theta prime, where theta prime is just theta minus mu b. And similarly for the fermions, and so this K is just of the same form as the H, but now with the primed kinetic terms. And so the grand canonical trace is trace e to the minus beta k times an operator A. And so if all these objects exist, we just define the ensemble this way. So the partition function is the expectation of 1. And now since we have a tensor product space, we have to discuss how we take the traces, and one can of course take the traces successively. We will take the trace over the bosons first, and so this means we take the operator, if B is some trace class operator on the total Fock space, we take 1 in the boson space times this combination on the fermion space, where the etas are an orthonormal basis of the fermionic space. And this means that this bosonic trace, as I wrote it here, still is an operator on the fermionic part of the Fock space. And it's of course independent of the choice of bases I took. And if I get the total trace, I can iterate it in this form. Okay. And so here is a theorem that finishes the preliminaries. You can show that this operator is bounded below, and because it's bounded below and symmetric densely defined, you can use Friedrich's extension to extend it uniquely to a self-adjoint operator on the whole space. And its domain of definition is the same as that of n, so it carries over to h of theta itself. And then the full Hamiltonian is bounded below, provided that our kinetic term minus the chemical potential is at least some positive mu star, so bounded below by mu star times unit operator. Then this is bounded below by the number operator times mu star over 2, minus 2 pieces, well, minus this plus that. That is just the fermionic part, and that is also a purely fermionic operator, because remember the G's are just made up of fermions, so they act on a finite dimensional space. So these are two bounded operators, and so this is at least n minus 2 bounded operators. And because of that, one then knows that if you take any polynomial in these creation annihilation operators of the bosons, this thing is trace class on the whole space. So now this is, I don't know, didn't look up the literature. It's very easy to prove. The essential points are that if theta prime is bounded by mu star times the identity, then we have this inequality, and so the whole Hamiltonian is bigger than hb of mu star. And if you look at hb of mu star, then you can just complete the square. And so completing the square gives you the thing that gets subtracted plus some positive object. And so now you drop this and get an inequality in this way. So this is bounded below. And the reason why the traces converge, I mean, when we now go back to this here, is that we have this NB, and the spaces are of course graded by NB, so we have to worry only about the dimension of the space, and the dimension of the bosonic space is what I wrote earlier, and you see that because this binomial factor grows only power-like in n, the exponential suffices to control it, and then the trace converges. So, okay, so these are the preliminaries, and now we start rewriting this as an integral. For this we introduce the coherent state. And the coherent state is made such that it is an eigenstate of the annihilation operator for the bosons, and the eigenvalue can be any complex number. So for any complex number phi, there is an eigenvector, namely the v phi, which is given by this formula here. And so you can ask yourself, why is this defined? Well, you just work out that this exponential here has a finite radius. Well, it's an entire function, simply because if you expand it, this thing here is only square root of n factorial. So the exponential series gives you an entire function. So the coherent states are anti-analytic functions of these complex variables phi. And if you use that, you can easily prove this identity just by commutation of powers, and this by sorry. So, and then we plan to use these phi's to rewrite the bosonic trace in terms of an integral. And this is, of course, known, has been known for a long time in the physics literature in a formal way. And so the results I cite here are from this paper of Balaban, Feldman, Knörrer, and Trubowitz. It's very simple, but it's very nice to set it up this way. This, if you omit for a moment the index r here, this looks like the standard formula that you would write down as a resolution of identity, which you find in physics textbooks, except that this formula is divergent because one integrates something of norm 1. And so what one does here in this integral is one restricts the integration to a disk with a two-dimensional measure, and then one can show that this converges to the unit operator strongly. So when it's applied to any vector. And moreover, if B is trace class, then one can calculate the trace of B times 1r as this integral, where B gets sandwiched between these coherent states. And this really converges to the trace one wants to get when one takes r to infinity. Sorry, something. Okay. And since I was discussing the bosonic trace, there's a variant of this formula where you trace only, well, we have a tensor product, so the analog of the bosonic trace formula gives us an analog by integration formula. So these double things here just means you keep the fermionic part as an operator. And one gets this for the trace. Now we have set up things such that we can just do the usual trotterization. Well, we don't do the usual trotterization here. We do it slightly sort of improved. So you know the trotter product formula tells you that since we have an operator which is bounded below, we can decompose it in these pieces and write this pth power of these exponentials of 1 over p times the summands. And I add in here a term of 1 over p squared because it's going to be convenient afterwards. And so, I mean, it's just the standard thing. You now use this formula because it's strong convergence. The trace can be written as the limit p going to infinity of the trace of this times some observable p. And then one just inserts in between each of these two factors the standard resolution of unity, but with a cutoff r. And then you get this formula here. Yeah? So it's a very simple formula. We get this matrix element, which still is a fermionic operator, and we get these two factors here. And all we have to do is calculate this. So it's very simple. Okay, so then now here's the curiosity of the whole algebra one does, namely if you have the matrix element of some quasi-free operator, so e to the minus epsilon times something quadratic, then it turns out that you get it in very easy way. You take e to this quadratic form in phi bar and phi prime, the vectors that appear here, but you get e to the minus epsilon theta prime in the exponent. That's just the way it is. You just have to do the algebra, the expansion. It's very simple. And well, if you now take the fermionic operator and you do the same for the bosonic Hamiltonian, you will remember this has three pieces, namely this one and then the ones where this operator couples to the B and the B dagger, and you do the same completion of the square as before. And because these are fermionic operators and they are normal, this means that these things have the same commutation relations as the B's. And so you can just use the same algebra and you get immediately that e to the minus epsilon hb is this quadratic form, but with the phi's replaced by phi plus g dagger and phi plus phi prime plus g. And then you run it, well, you just expand it out and you get all these pieces, and these 1 epsilons and 1 epsilon squared are just 1 up to order epsilon or epsilon squared. And so now we see that we have one piece which we, well, we can get rid of this piece by choosing R. R was the thing we added into this formula, subtracted it, so we can get rid of this piece here by choosing R to cancel it. And with this one then gets the following result. We also collect all these terms, so these e to the minus epsilon theta prime terms with the diagonal terms which appear in this formula, so with this type of terms here, and one gets a Gaussian measure in the bosonic fields. So here is the quadratic form in the exponent. So this comes from the coherent state integrals, and this comes from the just discussed matrix element. And we have also a term connecting p to 0. So the p time slices close up periodically. And this may look weird, but if you look at the covariance of this, I mean, suppose R went to infinity, so we have really a Gaussian. And it turns out the covariance is really just the continuum free boson two-point function. So in other words, you have this function which is explicit, a time-ordered function with a jump at 0. And if you want this covariance, you just plug in the tau q's. And I guess the only thing I never wrote down is what tau q is. So tau q is q over p times beta. So q is between 0 and p. And so this is nice and convenient. It's because of this exponential here that one gets actually a result which is basically like in the continuum. It's a straightforward discretization which one gets this way. And but there is still the cutoff R in the measure, so it's not really Gaussian yet because we still restrict our phi's to a finite disk. So if we introduce the notation that this integral with this cutoff Gaussian measure is just this angular bracket with dp down there, then we can write the result in the following way. So the bosonic trace is given by some prefactor times this product of fermionic operators. And so it all looks very nice. The point about this product is that these are still non-commuting operators because the interaction term doesn't commute with the fermionic kinetic term, of course. So we want to, we still are in a non-commutative setting. And so that's why we introduce a Grassmann integral for the fermionic trace. And I will not go into the details. I will not bother you with them. formally it all looks completely the same as for the bosons. It's just in reality very different because everything is antisymmetric instead of symmetric. But you get exactly the same stuff. So you get these quadratic forms get exponentiated a second time. And instead of the bosonic two-point function, you get a fermionic time-ordered two-point function. And now the only weird thing about it is if you now do this and you take your nice linear coupling of the phi to f dagger f, it suddenly ends up in the exponent of the exponent. And that looks really bad because we just have a Gaussian measure, and now apparently we have e to the minus epsilon phi up there. Which of course we have a finite disk over which we integrate, but this is not going to look good for the limit r going to infinity. And nevertheless, it is correct to just expand it down and take the lowest term. And so this then becomes an expectation. So the statement is one can take the limit such that this exponential is not there, it's replaced by its first order term. And the expectation is now in a fermionic Gaussian integral and a bosonic Gaussian integral. So that's the main statement. And so the question is, why is this so? Certainly you don't get it by naive expansion, but if you think about it a little bit, I use an expression that Joel Feldman used a long time ago. Pauli writes to the rescue. So basically this is not really a problem because these Grassmann variables are nilpotent, so an exponential of this type is really just the product of 1 plus these bilinears. And so you see the thing isn't really in the exponent. It's just when you expand it down, it just comes down. And now it looks as if the exponent is again linear in phi and phi bar. I just wrote the phi bar part here. There's a factor for the phi's as well. So there it looks as it should be okay. But it's not completely trivial to implement this because this set here is a set of all time slices, and so the set depends on p. So if you do your estimates stupidly, then you will get a p behavior which prevents you from taking the limit. And this is actually the one part in the proof where one has to be a little bit careful, namely doing the estimates right, so that one can show that one can make this replacement and resum this expansion. And why is it not completely obvious? Well, first of all, we have an integral still over a disk in phi space, so what we can now just put in absolute values. And if you look at the Gaussian integral for the bosons, one can of course do this in this way. You just take the absolute value, so you get the real part of the exponent, and the real part of exponent has a decay, and the decay is proportional to this mu star, which is this lower bound for the kinetic term for the bosons, times 1 over p. So it is very non-uniform in p, but it allows us to take r to infinity. And once we have taken r to infinity, we go back to the original expression, and we avoid putting in absolute values because the integral is oscillatory. So for the Grassmann integrals, we have a determinant bound which we use at the end. For the bosonic integrals, we don't use any bound for the moment, but we just expand it out completely. So we expand it to infinite order, and use the fact that bosonic integrals are permanents. And permanents, of course, do not have good bounds. You get a factorial when you try to estimate a permanent, so you can't really do better than taking, if you have an nth order permanent, have n factorial times the maximal value of this matrix element. This maximum value is finite because we have assumed that theta prime is positive. I mean, this Bose function is also something unbounded in principle, but if you have a gap, then this is finite. And so you have to deal with this factor n factorial, and well, this one just has to do. And of course it works out because the coupling is linear in phi, so the exponential gives an anti-analytic function. So what one does now is I don't write the formulas out there very long, but the idea is you just do the expectations, you estimate the permanence, and you estimate this factorial by decay of the other factors, and then you use a determinant bound to bound the fermions. For the fermions it's particularly simple because you just I mean, the determinant bound for these models is simply 2. So for every field psi which appears in your integral, you just put the factor square root of 2, and so you have to just count them and use an appropriate norm. Actually, I've written down the norm here somewhere. So you just use a norm on the Grassmann algebra which obeys the product inequality, and where you have the inequality that the expectation with the Gaussian measure is bounded by this norm. And once you do this, you can bound the Grassmann part in a very simple way. So there's nothing complicated needed there. Okay, so in the end, what one has, and that was also what is expected, you have the fact that you can map this theory, which is quadratic in the operators, also to an integral which has an exponent which is at most quadratic in the bosonic fields. And now we can go and do this. And we can now, of course, do the Gaussian integral over the bosons, and we get an interaction of this type. I mean, the Bose propagator is non-local in time, so we get an integral over 2 times with the fermionic fields, and this giving some kind of retardation effect. I've written it here already in continuum notation, so epsilon times the sum over q is some integral over tau. And starting from this formula, one can first of all generalize a few results we had recently. So in a recent paper with Wojciech Deruk, we proved persistence of exponential decay of truncated correlations. One can generalize in the limit beta going to infinity. At finite beta, one has to be a bit more careful because there's some p0 equal to 0 term in it. And so this is standard fermionic technology which is being used by many people. So I won't expand on it here. If you want to know it, you can read in this paper. There's a simple exposition. The important thing maybe since it's such a general result for gapped systems, is that it also doesn't require translation invariance. As I said, the determinant bound, which is one of the essential things that enters there, it's finite for any self-adjoint Q. It is 2, no matter what Q is. And the 2 is related to the fact that we have a unit lattice convention. If we had tried to take the continuum limit, let's say take a lattice of spacing epsilon, then it would be 2 to the epsilon minus d half. so it would diverge as epsilon goes to 0. Okay. So have we gained anything for the original model I wanted to study? Well, that model is actually gapless. So the matrix theta, when you now assume translation invariance and take the Fourier transform, it very much depends on what your situation is for this Fröhlich Hamiltonian, namely what type of spectrum these phonons have. And something you always have in a solid are acoustic phonons. They are Goldstone bosons of translation symmetry breaking, and they typically have a dispersion which is linear at small k, so some velocity of sound times absolute value of k. And for these phonons, the chemical potential is also 0, so you actually do have a 0 mode in your theta and theta prime. And however, the fact that in this model the coupling to the fermion density also vanishes at k equal to 0, this is this little bit peculiar factor square root of omega k, which is in front of the coupling constant, means that this 0 mode decouples and one can prove the convergence of the time continuum limit similarly as before. But then, of course, now the real problem starts. You want to analyze this theory. So G is real, and you see that one has G coupling to G bar. So you see when the G is real, then these are the same objects. So this means that this quadratic form symmetrizes effectively this function here. When you symmetrize the function, you then get this type of interaction in momentum space. And so what we actually have shown, and this is the part where renormalization and much technique comes in, one can show that vertex corrections, which are related to the expectation value of B dagger F dagger F. Well, let's put P's and Q's. That these are of the order C, where C is this speed of sound. And this is called Migdal's theorem. Migdal had it in the 1960s, but there was no proof of it. Now, why is this so important? The speed of sound is proportional to the square root of the electron mass over the ion mass. And if you work out the numbers, let's say for lead, you get a factor which is 1 over 400. So if vertex corrections are very, very small, then a certain set of so-called Schwinger-Dyson equations almost closes. So you get a very good approximation to the full theory by considering just a set of two integral equations. And that is the deeper reason why the BCS theory is so accurate. And so for this reason it is interesting to prove Migdal's theorem. Okay, I mean, proving it in perturbation theory is one thing, proving it non-perturbatively is an entirely different thing. The functional integral we have derived here may be useful to do this. I think this is a doable problem. About the proof that superconductivity exists, I will not make any remark. And so let me just come to the end. So, I mean, what I showed you was an exercise. It was not really very hard, but it was surprising that you can find out that you seem to run into obstacles, but it all works out very nicely when you use the techniques we have. And the derivation did not assume in any way that the interactions are weak. It gives us something I didn't talk about at all. It of course implies also that we can choose our discretization from a wide a variety of discretizations by discarding order epsilon squared terms, and that may be very useful in just studies that are not completely expansionists. Now, if you remember the beginning of my talk, I had started with two Hamiltonians. One was this electron phonon, and the other one was this with the quartic Bose-Fermi interaction. This is a technically interesting case because it's borderline for the expansion that we used here. I mean, if you remember, the idea was if the coupling of phi to the fermions is linear, then you have an anti-analytic function. Now, if it's quadratic, you can expect at most a finite radius of convergence, and then you can start trying to work it out so that it converges. And this requires a number of tricks, actually, to do it. Okay. I think I'll stop here. Thank you.
Are there any questions? Yes.
At the beginning, your bosons and fermions were, I think, non-relativistic. What happens if you make them relativistic with a linear dependence?
Oh, for the fermions, see, for the fermions is okay. So what I wrote down is for the bosons. At the end, I did write omega of k c times k. So this is not quadratic anymore, anyway, right? For the fermions, I didn't specify anything because it actually doesn't matter so much whether they are, well, let me say it in stages. For this argument of convergence, this doesn't matter at all. So you can also take, for instance, graphene as a lattice system, and then you go to the pure case where your Fermi level is just at the tips of these two cones, and then you have a linear dispersion. Yeah? The real analysis actually comes when you try to prove decay estimates. Then it makes a very big difference whether you are at the tip of the cone where your singularity is point-like, or whether you have an extended Fermi surface. And then it very strongly depends on that. But in principle, the case where you really have a point-like singularity is, from the power counting point of view, simpler than the general case.
Yep.
Is for this last problem you mentioned, is there the sign of the interaction between the two?
Of course, I mean, it has to be repulsive, otherwise it wouldn't even be stable.
The result is then somehow quadratic in the interaction in leading order, or?
No, actually, you have to arrange things that the important term is e to the minus g times epsilon times phi squared. Yeah.
Mm-hmm.
That's the hard part.
If there are no further questions, let's thank Manfred again.